we'll go ahead and get started with the extraction lab. So there's quite a bit to talk about, and it's pretty easy to get some stuff confused and shuffled. So if you've got questions, slow me down, that kind of thing.
This is the first couple questions. Sorry, we're talking about this.
Okay, solubility. Yeah, I know. What we guys have already seen as far as your solubility is like forces dissolve like forces. So what we're going to try and do is apply some of that solubility knowledge and try and take that a little bit further to do some more purification schemes. Okay? And when we talked about recrystallization, we said recrystallization could be a separation or a purification. We said it was better as a purification. And the limitations on that came down to what you can remove. Okay, so when it comes to recrystallization, you can only really remove small amounts of impurities. If you've got a lot of impurities, you have to rely on huge differences in solubility. Okay, and that's usually fairly rare as far as solubility goes. Okay, so small amounts of impurities, if you have similar solubilities, or really large differences in solubility. Okay, so it's a bit tricky to get the recrystallization to work right. Okay, so what we're going to try and do now is see if we can't change our structure around a little bit to change our solubility and allow us to get a better separation or a faster separation than a recrystallization would do. Okay, so what we can do is kind of pump through a quick example. If we took a look at water and diethyl ether, so on the bottom, we've got water and diethyl ether there. Okay, as far as solubility, would we expect those to dissolve with each other or mix? To do that, what do we have to do first? Nothing? We want to look at our intermolecular forces. So with water, what intermolecular force do we have? And with diethyl ether, that one's a little bit trickier. We do have a dipole, and I'm also going to write the LDF forces there. Of those two, which one's going to dominate the intermolecular force?
LDF.
Okay, we're going to get LDF for a couple reasons. What's our primary reason? We've got at least 4 carbons to outweigh a single hydrogen bonding interaction, and we have a dipole-dipole, which is even weaker than a hydrogen bonding. Okay, taking a step further, those carbon bonds can freely rotate. So if we started to build a hydrogen bonding interaction between diethyl ether and water to cause it to mix, the single bonds could rotate and smack the water molecule out of the way. So we minimize any interaction that's possible there. Okay? So we would expect 2 separate layers. Okay? Because it can be difficult to refer to each layer by its name, we'll sometimes switch that up, particularly if we switch between using a different organic solvent. So typically we'll call it our organic layer and an aqueous layer. Okay? If we were going to try to then dissolve, benzoic acid, so the compound now down below, where would that compound likely be most soluble? In the aqueous layer or our organic layer?
Aqueous though.
Okay, why would you say aqueous?
It has hydrogen bonding.
We do have a lot of hydrogen bonding out there. Except, what else do we have a lot of? We've got a lot of LDF coming from our ring. Okay, that ring dominates our overall structure, and we see primarily LDF forces for our compound. This compound primarily acts as an organic compound, and we see organic solubility. Okay, you guys went through and did a recrystallization with benzoic acid last week, and you used water as your recrystallization solvent. Okay, the reason water worked was because we could change the solubility, and primarily it was insoluble. That's how you got your compound back out. Okay, so we do have the experimental evidence to support what we're guessing at here. Okay, so the idea now is that in an extraction, we want to cause that compound, our benzoic acid, to switch from being organic soluble to becoming aqueous soluble. Okay, so we need to come up with some kind of method or some little bit in between to change the solubility of that compound. Okay, and that's where this technique gets a little bit trickier. Okay? So let's go through and start to look at some more issues with it. What we're going to try is active solubility. So it's chemically active. We're going to chemically alter our structure to try and change its solubility in the individual layers. Okay, so we just said diethyl ether and water don't mix. If we put them into a centrifuge tube, which is what you guys will primarily be using for this lab, okay, we would expect to see two layers. Which layer is which?
The aqueous is on top.
Okay, why would you put the aqueous layer on top?
It's less dense.
Okay, so you're coming to the right point. We need to know the density of each of these compounds. Okay, how would you ever find the density of each of the compounds? What's that? So it's not going to be molecular weight. Okay, it's something that we're actually going to have to look up. Okay, I'm not referencing it, and if this wasn't recording, maybe that statement would make a little bit more sense. Wikipedia works as a really good source. So if you ever don't know the densities of your individual compounds, you can go to Wikipedia and look those up and figure out what the solubilities are and try to apply them appropriately to figure out these layers. And what we end up finding out, sorry, Alex, you were wrong. Diethyl ether is less dense than water, which means it stays on the surface. Okay? So we now have these two layers. Okay, we're going to look at a new compound. In this case, we're not going to look at benzoic acid. This one I think is a little bit trickier, which is why I decided to work with this one. Where would we expect this compound to be soluble? Our organic layer or our aqueous layer? So what would we have to evaluate? What are we looking for to determine solubility?
The kind of forces it has.
We need to look for intermolecular forces. Okay? So if we take a look at this compound, what intermolecular forces do we get? Everything except ionic. We get hydrogen bonding out here. We get some dipole in here. A lot of LDF here, a lot of LDF here. Which intermolecular force is going to dominate? No, it's a bit tricky. It's a big hint. Our London dispersion forces end up dominating the overall solubility of this compound. It ends up being highly organic soluble. Okay? It does have some polar features within it, but those features are overwhelmed by the LDF structure itself, okay, or the rest of our nonpolar covalent structure. Okay? So we now want to come up with some kind of system in which we can change the structure of this compound to try to make it more soluble or differently soluble. Okay, so we want to increase its solubility in water. Okay? To do that, we need to change the structure. How could we change the structure to make it more water soluble? What intermolecular forces does water have? Hydrogen bonding. So what's a good option to make this compound more water soluble?
Add hydrogen.
Let's add not just hydrogens.
OHs.
We need some polar functional groups on this. Okay, so we could add a bunch of OHs to this. That works. That's going to drastically increase our water solubility. However, how easy is it to put an individual OH on that carbon? We'd have to break off a hydrogen and then somehow attach the OH to that carbon. Okay, that involves a lot of different chemistries, not particularly easy. Okay, and we want something that's relatively easy. So, what chemistry have you seen so far in your chemistry careers? Very subtle hint.
Acids.
You've seen acid-base chemistries. Okay? Why have you seen acid-base chemistry? Okay? In general, it's very simple, it's very fast, very easy. You add it, it does its thing, it's very visible, all around just easy to work with. So if you look at the chemistry you did in Gen Chem, a lot of it was acid-base based, and that was because it's very easy, simple chemistry to observe. Okay? So if we're going to take advantage of that, we need to come up with some way to be able to look at our molecule and decide how will it react. Will it react with an acid or will it react with a base? Okay? This gets a lot trickier, a situation that I'm probably not going to spend a whole lot of time on and not do it anywhere remotely near the justice it needs to be fully explained. Okay? So to start, we need to know what definitions we're looking at. So what is an acid? Okay, so you picked the definition that I actually wanted you to pick. We can look at it acting as a proton donor. What charge is a proton? Positive, typically symbolized by what symbol? It's not just a plus. No, not that either, but good call. H plus. When we're referring to acids, we're looking at the transfer of H plus from one place to another. Okay, so when we say proton, we're really referring to a hydrogen ion, which is effectively a proton. Okay? So what we're concerned is how that atom can get positive. It needs to be H plus. Okay? Hydrogen starts with a single electron. So how do I get that single electron away from that hydrogen?
Give it to something that wants it.
Okay, what's something that wants one? What kind of thing would take an electron away from a hydrogen? Okay, we could look at a base, except a base is actually going to do the opposite. It's going to give electrons to the hydrogen. Okay, kind of the right idea. We want to look for something simple and easy to deal with. What kind of element would take electrons away from other elements? Electronegative elements. So we can look at our halogens, oxygen, and nitrogen. So we got our halogens here. You got your oxygen elements, and then you got your nitrogen elements. Okay? And if we went through and looked at our acid-base strength, our halogens, most of them are strong acids, actually defined as strong acids, the one exception being HF. When you look at oxygen, we look at OH bonds. Are they acidic or basic? Take a look at water. Is water acidic or basic? Trick question. It's both. It can act as an acid or a base. It has the ability to do both. Okay, so our oxygens, so we get strong acids with our halogens, and our oxygens act as acids or bases. Okay, so what happens when we move to nitrogen?
As a base.
Okay. Its electronegativity is not enough such that it can completely take the electrons away from hydrogen, which means the lone pair on nitrogen, instead of nitrogen acting as an acid and taking them away from hydrogen, it ends up sharing its electrons more willingly, and we end up seeing our nitrogen elements act as bases. Okay? That's something you're ultimately going to have to memorize, okay, as far as those reactivities go, because there isn't a nice way to explain that. What's our definition of a base? Proton acceptor. I heard you whisper it. Okay. So now that we've got and for it to be a proton acceptor, what does that atom have to be able to have to pick up a proton? What charge is a proton? So you answered the first question. Our proton acceptor needs to have electrons. Okay? And in particular, lone pair electrons is our most common case. So we can now take these two definitions back to our structure and try and decide, do we have a hydrogen bound to oxygen or a halogen? No, which means our structure, that's the next step from it, but I wanted to go with not an acid first. Yeah, I know. Okay, we can't necessarily say it's a base directly off. We then have to go through and evaluate our base definition. According to our base definition, we have to have electrons present. So it's not just that it has a nitrogen. Do we have a nitrogen with lone pair electrons?
Yes.
Yes. So we do have a compound that can act as a base, which means what we can do is react it with an acid. Okay? In theory, you guys are comfortable with mechanisms? How much of a theory is that? pretty big theory, I guess. Okay, judging by the overwhelming response. Okay, so what we want to do is come up with a way to represent how this reaction is occurring. Okay, if you look at a Gen Chem textbook, this is almost always what they show. Okay, so they add that arrow. What are they showing by that arrow?
The hydrogen is bonding with those.
With the nitrogen. Yeah. Okay, which seems reasonable enough. We're showing the flow of something that we still can't see, but we at least have a symbol for it, moving from one place to another. Okay. The problem with that is that when we're looking at organic chemistry, what did we say was the most important thing way back at the beginning? The electrons. By showing the arrow in that case, we're showing the flow of a lack of electrons. That doesn't make sense. Your arrow always, always, always must start wherever you have electrons and end someplace where it's lacking them, or it's pulling them away towards. So if we were going to draw this out as an answer, the most common answer might be something along these lines. Okay, is that correct? Doesn't seem like it, and I'm saying a shaking head yes. Okay, we have shown where that hydrogen went. It's now attached to the nitrogen. Also in that process, the nitrogen lost electrons, started neutral, loses electrons, so it's now positive. That makes sense. What happened to the nitrogen-carbon bond? Did I do anything with that bond? Did those electrons change? No. How about that carbon-carbon? Or that carbon-carbon double bond? Nothing happened to those. And yet somehow when I look across this reaction arrow, they aren't there. So when we draw out an overall reaction, we must show all of those pieces. Okay? If nothing happened to it, that's fine. You just get to draw out that nothing that happened to it. Okay? I know it's tedious, but you have to go through and do that. Okay? Why is this important? Okay, well, what happened to our structure now? If we evaluate our compound, what intermolecular forces do we now have? What's that? We have H bonding, but we had H bonding before because we had a hydrogen bound to nitrogen, oxygen, or fluorine. Anything else happen? That's a yes.
It became more ionic now?
Yes, it became more polar, and it's ionic now. How do you know it's ionic? Because it has a charge. As soon as we pick up that charge, we now have an ionic compound. That drastically changes our intermolecular forces. Okay? Where have we seen ionic compounds before? Salts. Favorite salt? What can you tell me about the solubility of sodium chloride? It's extremely soluble in water. Okay? The ionic intermolecular force is so strong and so polar that regardless of the rest of the structure, water will dissolve it. Okay? So as soon as I generate that ionic bond, I now have something that is water soluble. Well, how did I start? I started water insoluble. Okay? So just by the addition of an acid, I can change my structure enough to change the solubility. With the solubility now different, I can now separate my organic compound away from its organic solution. Okay? Does that kind of make sense? So before we push that a little bit further, why do we use acids and bases for extraction? We already talked about some of these. Simple, fast, reversible. It's predictable. Okay, so if we add an acid to a solution or we run an acid-base reaction, we typically get a salt and a neutral compound. Okay? The salt is ultimately what we want to happen for our organic compounds to change the solubility and make them now water soluble. Okay? If you're ever put in a situation where you don't know what's going to happen, okay, or you're trying to figure out which acid is the strongest or weakest, or where your what position is the most basic. Okay, if we go back to just this compound and I add an acid to it, and you don't know that that nitrogen is basic, okay, hopefully you do know your base definition. Okay, and the base definition is that we need electrons to share with that hydrogen. Okay, Well, what happens? Where do we have electrons to share with that hydrogen? Good answer. On the nitrogen and our oxygens. So what we can go through and do, and this is extremely tedious, is draw the product of all of those possible atoms reacting with the hydrogen. And we end up with 3 possibilities. Okay? Within those possibilities, we can try and evaluate stability, which of those is the most stable or the most likely. If we find the most stable one, what does that mean about what's our most likely reaction? It's going to push to the more stable product. Okay? In this case, we can simplify a little bit further. We can say we're looking at nitrogen versus oxygen. Okay? One of those 2 elements has to share electrons. Which element is more willing to share electrons? Nitrogen, why?
Less electronegative.
It's less electronegative. Oxygen's more electronegative. It's holding those electrons. It does not want to give them up. We would predict the nitrogen to act more basically. Okay? The other thing that you'll hear me refer to fairly often throughout the semester is what I would refer to as the phase test. Okay? So given an option, we can go back to kind of our simple examples. We take a look at this situation up here. Okay? We want to go through and pinpoint the most dangerous thing. So we can compare water to HCl. So let's pull a face test. Which one would you rather have splashed in your face? Water. So HCl will be our reactive dangerous species. That'll be our acid. We'll now go to our products and evaluate the same thing. Which would you rather have splashed in your face, H3O plus or Cl minus? Cl minus, probably Wednesday night, you might have all over your face already.
Why?
Your exam.
So what?
What did I just box in? Salt. Where's chloride coming from? We find it everywhere. It's in our tears. Okay? So now given the choice, do you want H3O plus, which we know to be an acid, or chloride? Chloride's a lot better, so we're looking at H3O plus being our reactive species. Okay? Just based on that, we were now able to determine what's more reactive in each of those pairs. We can take it even further. Now we want to decide which way our reaction goes. Do we stay as reactants or do we move to products? So we'll compare the 2 things that were the most dangerous. HCl versus H3O plus. This is where neither of those we particularly want splashed in our face, but if not given the choice, which one would we rather want in our face? This relies on you knowing some definitions.
HCl's worse, right?
HCl is worse because it's a strong acid by definition. So it is extremely acidic. H3O plus is an acid, but it's slightly weaker. So given the choice, which one do you want splashed in your face? The weakest acid. Chemistry does the same thing. Where does our reaction go? Towards our products. Okay? So we can use a lot of those definitions to predict if a reaction is likely to occur or not likely to occur. It can help out a lot as far as that goes. Okay? So, some other things to watch out for when trying to predict chemistry, particularly when looking for acid strength. Okay? We just talked about comparing the acid to our conjugate acid, so across our reaction. We can come up with some qualitative rules for determining which acid is stronger or weaker. So if we take a look at the generic acid HX, the larger X is, the larger that X atom, the more acidic our hydrogen was to begin with. Okay, so if we compare HCl to HF, which one's the stronger acid? HCl, because atom X in that case is chloride, which is larger than the fluoride on it. Okay? The next thing we could do is look at electronegativity. So if we compare or look at atom X and try and determine acid strength. So if I compare water to methane, so OH to CH, which one's more acidic? OH. Okay? Because oxygen is more electronegative than carbon. Okay? Where this becomes tricky, let's go back to HF and HCl. Which one's more electronegative? F. Which one's bigger? chlorine. There's an issue there. There's a mismatch. Okay? If we go based on electronegativity, we would say HF is more acidic. If we go based on size, HCl. So which one trumps? Size. Okay? Which is why I put it first on this list too. There are other rules. In theory, you saw them in your lecture. If you didn't and need help, you can talk to me about it, and I can help you out with that. But these two are going to cover 70-80% of the cases that you'll see throughout the semester. As far as the lab goes, this is the only lab you'll see the quantitative rules show up. You can look back to KAs and PKAs. So the biggest KA is the most acidic. The smallest pKa is the most acidic as well. Okay? So looking at those numbers, you can do quantitative comparisons to just decide where your strongest acids are. Okay? And then as we said already with the phase test, the side with the weakest acid is the one that's favored. Okay, so how can we now use this information? So to start off with, we've got kind of a key in the upper left-hand corner to describe what's happening, or all our individual structures that you're going to be dealing with for this lab. Okay, because drawing those structures out, for me, is going to be a bit tedious, I came up with abbreviations. So we're going to start off with a mixture of HA, B, and N. Okay, so those are all in one container. Okay, for this reaction to work, I need to make sure all of those get dissolved. They're all organic compounds. They're all dominated by their London dispersion forces. So I'll add an organic solvent, diethyl ether. Now they're all dissolved. But if I'm trying to separate them, I need to put something else in there to cause them to separate. What could I add? What wouldn't mix with diethyl ether? Makes up 80% of the planet. Water. Okay, what's the problem with adding water? Are any of your compounds soluble in water? No. So I can't add just water. I'm going to have to add something else. Okay, what's that something else? Is there any chemistry that I could take advantage of in those compounds? Say acid-base chemistry, where acid begins with A and base begins with B.
You can do either one, right?
Okay, pick one.
Acid.
If we add acid, what's your favorite acid?
HCl.
So we add HCl. What is HCl going to react with? A base. Which compound is our base?
B.
Probably B. That's why I picked these abbreviations. Okay? What happens if it acts as a base? It accepts protons. The structure ends up changing, and I get HB. Just HB, or should that be charged? Should be charged. Why should it be charged? It has an extra proton, which means the charge should be positive. Okay? What phase would HB be in? Organic or aqueous? Why aqueous? It's ionic. We've changed the intermolecular forces. It's now going to be soluble in our aqueous layer. Okay? What happens with our other thing? Well, we have an organic layer. So as soon as we add water, we get two layers, one with diethyl ether, one with our water layer. Okay? So we can now physically separate those away from each other with a pipette. Okay? And we now have those two separate containers. Our aqueous, we said, has HB plus in it. What does our organic have in it?
N.
So N represented a neutral compound. If it's neutral, what happens when you add an acid? Nothing, which means what happens to its structure? It stays the same, which means what happens to its intermolecular forces? Stays the same as well. What happens to its solubility? Stays the same, and will still be soluble in the organic layer. What happens when we add acid, HCl, to our organic acid?
It's going to be acid.
Still acid. Structure doesn't change. There's HA. Okay? I won't go through the rest of that branch up there, but we'll finish up the isolation. I don't want HB. I want to get B back. So my final answer has to somehow be B. How can I do that? How can I convert HB to B? What has to change?
H plus.
I have to get rid of H plus. So HB needs to act as an acid. What do acids react with? What should we add? A base. NaOH, what's its physical state? Solid, liquid, gas. So solid. Adding solid sodium hydroxide to anything is going to be a bit of a pain, particularly because you'd have to deal with the very concentrated sodium hydroxide tablets, which could easily burn you. So we typically come up with a better way to add it to a reaction. What do? We dissolve it in a secondary solution like water. So we end up adding aqueous sodium hydroxide. The sodium hydroxide reacts with our now acidic base, removes the hydrogen, and we're left with B. Okay? What phase are we in? Liquid or aqueous. Okay? To start off with, to get HB+, we were in aqueous. We then added more aqueous. Our phase is then aqueous. I don't think I spelled that right. Let's just do that. That's close enough. Okay? What does that mean about compound B? What would you expect to see?
It's going to be dissolved.
Should it dissolve? We're in a water environment. What did you say about the solubility of compound B? We would expect it to precipitate. Okay? So what you'll see when you do this experiment properly is you'll see a precipitate come out of solution. Okay? That would suggest that you did everything correctly and everything should be good and happy.
So that precipitate then is, again, an organic base?
That would then be back to our organic base.
Okay.
You can end up going through a similar process, I'll add another one just in case, with the organic acid to try and decide how to separate that one. Very similar idea. Okay? There is a YouTube video on dealing with filtration and for the extraction. The extraction goes through and isolates all three compounds. If you take a look at this previous slide, we had three compounds that we could potentially isolate. You only have to worry about isolating the organic acid and the organic base. Okay? So you won't have to isolate naphthalene. Okay? If you want to, you can push that the rest of the way and we can get you the procedure for it. But that's usually a bit much for you guys to do in the 2 hours. Okay? Filtration, you should all be fairly confident with that. I think there might be some other YouTube videos that might be helpful. I'll go ahead and get this lecture posted, hopefully in the next hour. Okay?